Welcome back to the second video on quantum computing. In this video, we'll explore the key components and concepts of quantum computers. This will pave the way for the next video, where we will create our first quantum circuit and code it in Python using Qiskit. Therefore, back to our initial question on how such a quantum computer can be programmed. What is the structure of a quantum program? What are the rules, possible operations, and how do we manipulate data in quantum computers? Before we start programming, let us start with 4 key cornerstone concepts of quantum computers. Need to look at qubits and superpositions, at the qubit measurement process, at entanglement, and finally at quantum gates, which we need for our quantum circuit. We begin with qubits, the core of any quantum computer. Quantum computers store information in qubits, not in bits as classical computers. A classical bit can be 0 or 1. A qubit can be in state 0 or state 1, or unlike a classical bit, also in superpositions of those states. A superposition is a blend of the basis states. It can be a state blended by 50% probability to measure state 0 and 50% probability to measure state 1, or 7% and 93%. Or whatever combination adds up to a total of 100% probability, as the actual measurement result can only be one of the two. Furthermore, each state of a superposition also has a phase. This phase allows quantum interference. Simplified, one can say that a state cannot just be 0 or 1, but it can also be -0 or -1. That means adding up 2 zero states with opposite phase will annihilate or cancel out each other. This is called quantum interference and is, together with superposition, the actual superpower of quantum computers. Now, we also need to understand the process of measuring a qubit. You cannot see the actual state of a qubit, but you can measure the qubit. Due to the measurement process, any superposition collapses into one of the base states 0 or 1, randomly but based on the probabilities of the previous superposition, and stays there after the measurement. We can read out the final base state and write the found value 0 or 1 to a classical bit. After the measurement, the qubit is no longer in superposition. Entanglement is another key feature of quantum computers. We will not use it for our first program, but it is still a cornerstone worth to be mentioned. Entanglement is more complex to understand as it involves more than one qubit. To really understand this, we have to look at multi-qubit systems in a later video. But in a nutshell, we can state this. 2 qubits can become entangled, i.e., they will not just have the same superposition afterwards, but they will also always result in correlated measurement results. For instance, in a 50% 0-0 and 50% 1-1 superposition, a Bell state, any measurement of the first qubit will randomly result in one or the other value, but the second qubit has no freedom anymore. It will show the same value as the first one. Programming a computer requires operations on qubits. Quantum gates manipulate the qubit states in predefined way, depending on the gate. In classical computing, there are many possible classical gates, NOT, or XOR and NAND, etc. In quantum computing, all gates must be completely reversible. That means information must not be lost. So an OR gate is not directly possible, for instance, as we cannot deduce the input bits from the output. A NOT gate is possible since it is reversible. The equivalent of a classical NOT gate is an X gate in quantum computing. Another key gate acting on single qubits is the Hadamard gate, which puts a qubit to a balanced superposition. So there are quite some differences in operators or gates on qubits compared to the classical gates. For single qubit gates, one can say that all these quantum gates can do 2 things. First, They can redistribute the probability balance between the states 0 and 1, and second, they might shift the phase of these states. The X gate, for instance, exchanges the amplitudes, including the phases of the 0 and the 1 state. Remember that in quantum computing, unlike classical computing, the gates do not operate only on plain 0 or 1 states, but also on any superposition. So, if you apply an X gate on a qubit in a balanced superposition, the result of a subsequent measurement will be the same as before, because you flip the probabilities between 0 and 1, which are both still 50%. For our Hello Quantum World program, we will use just one type of gate, the Hadamard gate. Okay, now you know enough to start coding. In the next video, we will create our first quantum circuit. We will encode and execute it in Python using Qiskit.